Hi students, today I am going to explain an important topic, aromatic electrophilic substitution reaction. So when we say aromatic, we remember benzene. So benzene is the most common aromatic compound. It contains 3 double bonds as we know. So all these 3 double bonds are involved in resonance. So it will easily undergo substitution reaction, and so when this undergo electrophilic substitution reactions, so this delocalized electron clouds of benzene will attract the electrophile, so that's why it will undergo electrophilic substitution reaction. So how we can define this electrophilic substitution, aromatic substitution reaction? So it is a reaction in which an electrophile substitutes a hydrogen. So it will actually substitute an atom that is nothing but a hydrogen, usually hydrogen, which is attached to an aromatic system, which is hydrogen attached to the ring of an aromatic compound. For example, when we see benzene, so benzene will be attacked with an electrophile, so it is substituted instead of hydrogen. So this is substituted benzene. So how it occurs? So what is its mechanism? When we see, it occurs in 3 steps. So what is it? First step is generation of electrophile. So first, before attacking, the electrophile should be generated, right? So the electrophile is generated is the first step. When we take this in the fast reaction, it is a reversible reaction. In this, electrophile and nucleophile are generated. So electrophile generation is the first step. After the generation of electrophile, it will be attacked to the aromatic ring, that is benzene, to form a pi complex. So what is pi complex means? So here the benzene ring will be attacked with the electrophile, and we cannot tell it at which position correctly. Just it will form a complex with the benzene. So that is pi complex, we can say. And this pi complex slowly again it will be attacked to the double bonds present there at different positions to form a resonance structures. Slowly it will form all the resonance. Here 3 resonance structures because of 3 double bonds. So after that it will form a resonance hybrid, which is also called sigma complex. So what is our second step? Formation of arenium ion. So this is called arenium ion, or we can call carbocation or sigma complex. So how it forms? First benzene will be attacked with the electrophile. Roughly it will form a complex called pi complex. After that slowly it will start delocalizing the electrons or attacking the electron cloud, delocalized electron cloud of benzene at one position. So here first it will be attacked to this double bond C. So and it will form complex, and this will be changing its position. So this double bond will be changing its position from here to here it will come. So here it will come. So again so positive charge here, again positive charge here, and this is shifted to here, this, and this is going to shift to here. So again so this is here, this is shifted to here, so here. So here positive charge will come. Like this the double bonds will be delocalized lastly to form a resonance hybrid like this. So this is also called sigma complex. So that is second step. And the last step is loss of proton from this sigma complex. From this sigma complex, so proton will be lost. So here proton will be lost with this. So with the nucleophile which is there, which is attacked. So here the nucleophile will take the proton, and lastly the electrophile will be there. So like this the substituted benzene electrophilic substitution reaction occurs, and the electrophilic substituted product is formed. So like this we can see, and we can tell the effect of the substituent groups, how it will be. So the effect of substituent groups, whatever are the substitution taking place here, electrophiles, how its effect will be, and it depends on the regioselectivity. So the next topic is regioselectivity in electrophilic aromatic substitution reaction. So let me explain this. Regioselectivity in electrophilic substitution, aromatic substitution. So we can say one thing, whatever is the electrophile which is attached to the aromatic ring, it may give two reactions. One is it may make the benzene ring or the substituted group faster or activating, or it may make it slower. So how it is? It depends on the region where the electrophile is attacked. So like this we can say, for example, the nature of the substituent already present in the benzene ring affects the rate and regioselectivity. Regioselectivity means region where, the position where it is there, the group substituent wherever it is present. So when a substituent is said to be activating, so we can say a substituent is activating if the substituent makes the substituted group more faster than benzene. So when we compare it with the benzene, the substituted benzene, whatever is the substituted group, it should be faster. When it is faster, then it is called, it is activating group. When a substituent makes the substituted benzene slower than benzene, when we compared before it is, then they are called deactivating substituents. So when it makes faster, then it is activating substituents or activating groups. So, and when it makes slower, then it is called deactivating substituents. So it will make the ring activating or deactivating. So before explaining this, I will just explain what are ortho para position, meta position and ortho para ratio to explain this detailedly. So what are positions? What is ortho position, meta position, para position? If we take benzene ring, so here double bond is there. So if we take first, second, I am counting the numbers along with the double bonds attacked. So double bonds present. So here it is double bond there. So 1, 2. So if we give numbering for this 1, 2. So wherever is double bond is there, we have to take numbering. So these two are ortho positions. So wherever is the double bond, here double bond is there, so it is ortho position. Here double bond is there this side, so this is ortho positions. So 1, 2. So 1, 2 positions are ortho positions. When we take from this side, so 1, 2, 3. So 1, 2, 3, 1, 3. So 1 and 3. Here when we count from this side, because double bond is this side, so 1, 3. So these are meta positions. These two are ortho positions, these two are meta positions, and when we count from here 1, 2, 3, 4, 1, 4, 1, 4 when we count from this side. So these two are para positions. Very easy. Ortho positions are wherever is the substituted, it is nearby are ortho positions. 1, 3 are meta positions. For opposite sides are para positions. Like this we can remember. So ortho para directing groups usually made the benzene ring more reactive. So when the substituents are attacked to the ortho or para position, then it will make the benzene ring more reactive. Remember this. When the substituents are attacked to the ortho or para, then they are more reactive. And this ortho or para will be in 2:1 ratio. So they will be in the 2:1 ratio. Then we can say For example, we'll take one example. So for example, we will check the relative rate. So this is trifluoromethylbenzene. So trifluoromethylbenzene, and this is benzene, and this is toluene. Trimethylbenzene, we can say toluene. So if the substituents, we can see here, when the benzene is attacked with the like toluene with the CH3, so it makes the benzene 20 to 25 times more faster. So it is activating. Okay. So when trifluoromethylbenzene is there, then it will make deactivating. How much times it will make deactivating? 2.5 into 10 to the power of minus 5 times it will make deactivating. How it is possible? Why toluene, when CH3 is there, why it is activating? When CF3 is there, why it is deactivating? It is explained here. So one more time I will tell. If the substituents are directed at the ortho or para positions, then they will be activating the aromatic ring. So they are activating substituents. If the substituents are directed at the meta position, then they will deactivate the aromatic compound. So they are deactivating substituents. So following this only I am telling the example. So see, toluene, I told it make the benzene ring 20 to 25 times activating. How it is possible? See, when we take toluene and we take nitrating mixture, so what happens? NO2 is attacked at the ortho position. I told 1, 2. So when that double bond is this side, so ortho position, this is meta position and this is para position. So we can see 63% is orthonitrotoluene, 3% is metanitrotoluene, para-nitrotoluene is 34%. So from this we can say 63 plus 34, 97% is ortho and para positions. So that is why it is an activating group. That's why I told toluene is activating. Then when we see trifluoromethylbenzene, so again nitrating mixture, when we substituted with it is substituted with NO2. So here orthonitrotoluene methylbenzene. So NO2 is substituted here. So it is only 6%. At the meta position it is 91%. At para position it is 3%. So we can say here 91% is meta position. So when the substituents are directed at the meta position, then it will be deactivating the aromatic compounds. That's why it is a deactivating substituent. So it is deactivating the benzene ring to 2.5 into 10 to the power of minus 5 times. From this we can tell, depending on the position of the substituents which are directed, so it may be activating substituents or deactivating substituents. So why it is happening? So because of the reasons like it may be because of resonance effect, or because of the structures, resonance structures it is happening. So let's see, if the electrophile is substituted at the meta positions, what happens? There will be very less resonance structures when we compare to para, or we can say when the electrophile attacks ortho or para, it will give a carbocation with more resonance structures. So finally I can tell, if it is attacking ortho or para, we will get more resonance structures. If it is attacking at meta position, it will give less resonance structures. So more resonance structures, more stable carbocation. So it is activating. Less resonance structures, less stable carbocation. So it will be deactivating. Like this we can explain. And activating substituents, what they will do, they will stabilize the cationic intermediate. So whatever is the intermediate formed, so these activating substituents will stabilize that by donating electrons to the ring system. It may be by either inductive effect or resonance effect. So that's why they are stable forms. Whereas deactivating substituents withdraw. So they are electron withdrawing groups. That's why they will be deactivating and they will not stabilize. So example of activating substituents are like toluene, aniline, phenol, etc. And we already discussed toluene. Deactivating substituents examples are like nitrobenzene, benzaldehyde, trifluoromethylbenzene. We already discussed about. Thank you.